Chapter 2 of Thermodynamics. This video is in no way intended to be all-encompassing. It is just an overview of some of the points. The things I skip does not mean that it is less important. It just means that you should be reading that in the book and that maybe it's more straightforward, but that what we're doing here is just covering the very main points and just an overview. So Thermodynamics, Chapter 2, this chapter is called Energy and the First Law of Thermodynamics. So the first law of thermodynamics is conservation of energy, and so that this chapter begins that discussion. So it's just a few notes about this chapter. That this chapter is limited to closed systems, when we talk about change in kinetic energy, change in potential energy, change in internal energy, we use the symbol delta, and that means final value minus initial value. So we are always going final minus initial. We work kinetic energy, potential energy, and heat transfer all have the same units. In SI, we have Newton meters, or else a Newton meter is also called a joule. And then in U.S. customary, we have foot-pounds or BTUs. Foot-pounds and BTUs, same thing. Newton meter and a joule, same thing. So we start by talking about kinetic energy. And kinetic energy is equal to 1/2 mv squared, where v is the velocity of the center of mass of the object that is moving, and m is mass. So delta, which is change in kinetic energy, is the kinetic energy at the second position minus the kinetic energy at the first position. So position 1 is the start, and position 2 is the finish, or the second spot we look at, the end. So anyway, we're taking where we end and subtracting off where we start. So the kinetic energy at position 2 minus the kinetic energy at position 1 equals 1/2 mass times the velocity at 2 squared minus the velocity of 1 squared. The work of a resultant force on a body equals the change in its kinetic energy. When the body is accelerated by a resultant force, the work done on the body can be considered to be a transfer of energy to the body, where it is stored as kinetic energy. So kinetic energy and work are related in this way. Kinetic energy is a property of the body. Kinetic energy is associated with the whole body, so we say that it is an extensive property. Potential energy equals the mass times gravity times z, where mgz, where m is the mass, z is the vertical distance, and acceleration due to gravity g is assumed to be constant. So again, the change in potential energy is going to be the potential energy at position 2 minus the potential energy at position 1, and it equals mass times gravity times the change in position, so z2 minus z1. Potential energy is also an extensive property, and we must assume a datum and a value for the quantity of the datum. Values of kinetic energy and potential energy are determined relative to this choice of datum. So when we consider change in kinetic energy, delta kinetic energy, and change in potential energy, delta PE, the arbitrary data reference specification is canceled. So essentially we need to draw some system where we are indicating where our datum would be. So if that's the ground, let's say, and we can assume that the ground is our datum, so we call this the datum, and I'm going to say z is up from here. We have to indicate our sign convention, indicate our system here. So let's say we just have some kind of projectile leaving from here, and then we have some body that is on that path, and that body has a certain amount of weight. So we have mg and so on. But this is where we took off from. So this is 1 and this is 2. And we use that datum. So we have to give the datum a value. So my datum is the ground, and I'm going to say it's 0. I can set it at anything I want. I could say it was 22.3 or 12 or 100 or whatever I want to set that datum as. I could set it at the elevation of the ground at where it actually is. It doesn't matter as long as we set it as something when we go through the subtraction, that datum, that value cancels from our equation. So it doesn't matter what you set it at, you just have to set it at, and then everything is relative to that position. It makes sense to set it at 0 because our calculations are a little bit easier. But if this is our datum, then Z1 would be equal to 0, and Z2 would be equal to this distance. And we can find the change in potential energy between those two. Conservation of energy in mechanics. So when the resultant force causes the elevation to be increased, the body to be accelerated, or both, the work done by a force can be considered a transfer of energy to the body where it is stored as gravitational potential energy or kinetic energy. It's one or the other. These causes. So a force that causes an elevation to be increased, a body to be accelerated, or both are considered an energy transfer. In the special case, so what this says is only true in the special case where the body is acted on by gravity, then kinetic energy plus potential energy, the change in kinetic energy plus the change in potential energy equals 0. So there's no net gain or loss there. So filling in what we know here, we have 1/2 mv squared, v2 squared minus v1 squared. That's the change in kinetic energy, right? This is delta Ke, and then plus delta Pe, mg times z2 minus z1. That would have to equal 0. Rearranging this equation, we get kinetic energy at 2 plus the potential energy at 2 equals the kinetic energy at 1 plus the potential energy at 1. Replacing those or seeing those values, we get 1/2 mv2 squared plus mg z2 squared, or z2, not squared, equals 1/2 mv1 squared plus mg z1. So this equation is the same as this equation. Energy can be converted from one form to another. For a falling object under the influence of gravity, the potential energy would increase as kinetic energy decreases. So if we have a ball and we're dropping that ball, let's say I have a ball and I'm just holding it up here in the sky. My datum, I'm going to say, is down here. This is the datum. We'll say this is 0. And let's say whatever this distance is, there's a certain amount of potential energy being stored with it just being, the ball being held up here. So let's just say the potential energy is 1. The ball isn't moving at this point, it's just being held in space there. We have some distance here, z. So the potential energy would be mgz, and we're just going to say that equals 1. At this point, because velocity is 0, the kinetic energy at this point would be 0. As this ball starts to drop, the potential energy is being transferred to kinetic energy. And then just immediately, infinitesimally close to the ground here, at this point, then we have Potential energy, Z would be effectively 0. So now potential energy is equal to 0, and kinetic energy is going to be equal to 1. It transfers as that falls. So let's broaden our understanding of work. That's what section 2.2 does. Work done by or on a system is evaluated in terms of macroscopically observed forces and displacements. And that work is, work equals the integral from S1 to S2 of F ds. So S is displacement. And we can just see that the work done on the system is equal to that integral. Again, we remember that the definition of an integral, or the physical representation of the integral, is the area under the curve. So we know that work is the area under the force displacement curve. The thermodynamic definition of work. Work is done by a system on its surroundings if the sole effect of everything external to the system could have been raising of a weight. In effect, a force acting through a distance. It doesn't have to have been a force through a distance, it just could have been. So this is the definition of thermodynamic work. So if you can represent it as a work through a distance, then we consider that the thermodynamic definition of work. Energy is transferred when work is done. Work is a means for transferring energy. Work W, so this is important, one of the more important parts that comes up over and over, but we often just say that we call this work, we'll say work, but this isn't really work, it's energy transferred by work. So this is, we should not call it work, we should be using the definition of energy transfer by work. It's a distinction that it matters, and as we go through, you'll see. But work is not a property of the system. When we say it's not a property, it's a non-property. And if you remember back to our definitions in the last chapter, the work depends on the process, and so it is not. It is a non-property. So the whole how it gets to where it's going, it matters, and so we can't just look at the endpoints and say, this is the state at these points, and not care about how it got there. For work, we really need to know how it got there. The sign convention and notation for work, I can't emphasize enough how important this is, how little bit tricky it is. So write it down. You will definitely have this on your first test, maybe every test that you have. Certainly to do anything from this point forward, this sign convention is very critical to all the work done in this class. So sign convention and notation for work. Work is greater than 0, so positive. The work done by the system on the environment or the surroundings. So this is energy transfer by work out. And then work is negative, is work done on the system by the surroundings. So this is the surroundings or the environment or something putting work into the system. And that would be a negative W. The convention is used throughout the book. To avoid confusion later, you will see that the direction of energy transfer is shown by arrows indicating the direction of energy transfer. Work is regarded as positive in the direction of the arrows. This is out of order, but I put it here for contrast because they're so important and they sort of go together. But the sign convention for notation for heat transfer. So Q is the amount of energy transferred across the boundary of the system in heat interaction with the system's surroundings. So heat transfer into the system is taken as positive, and heat from the system is taken as negative. So we have here, it's on the next page, but I'll just write it here too. But so a positive Q is heat transfer in, and a negative Q is heat transfer from the system. Let's see. Heat transfer from the system. So if you look here, we have work greater than 0 is by the system or out, and work and the opposite here. So Q less than 0 is heat transfer from the system, or this would be out or out. So they're opposite to each other, and that's important to note. Work done on the system or in and is negative, and heat to the system or in is positive. So they're opposite to each other, and yeah. So we'd have to follow through and keep watching that and keep working with that, and have it written down on your note sheet, and look back to it as often as you need to. So again, note the sign convention for heat transfer is the reverse of the sign convention for work, or energy transferred by work. This came from steam engines and other devices that developed a work output from energy input by heat transfer. So again, thermodynamics is, the steam engine and so on was when thermodynamics was really sort of came into being. And again, they're not found, we didn't find these things, we're not proving things, we're just noting that these things are there, and they seem to work, and our formulas seem to work, and our evidence and data we are collecting and watching the things happen has not disproved anything. Anyway, the other thing to note here is that later on we'll see in chapter 6 that entropy has a similar sign convention to heat transfer. So work and energy transferred by work and energy transferred by heat have opposite sign conventions, and entropy is the same as heat transfer.